Hello all of you. So, in the last lecture we have been discussing the idea of entropy being the driving force when we discussed the first and second laws of thermodynamics. In this particular lecture we will take that argument a bit further, and then I will talk about reversible and irreversible processes, and after that I will discuss the idea of thermodynamic functions. So, we already have established that if I look at any particular system, I always look with a surrounding, saying that the system plus surrounding makes my universe. Clearly, surrounding is huge in comparison to the system. And then what we established using the first law of thermodynamics is that the internal energy of the system plus internal energy of the surrounding is constant, or in other words we can say for any process the delta U for the system plus delta U of surrounding should be equal to 0. However, the entropy of the system plus the entropy of the surrounding should increase. In reality, there is a greater than equal to 0 thing. There is a possibility that a process does not bring in a change in the entropy of universe, or it is possible that entropy increases. What is more likely in all situations is that entropy is increasing for the universe. However, there is a special class of processes for which entropy of universe is equal to constant, and in that case we call the process a reversible process. So, essentially for a reversible process, we have S system plus S surrounding is equal to a constant value, and we always talk about changes in the entropy. So, more precisely the previous expression would be delta S and delta S, where we always talk from a reference state when we define a process. So, we talk about changes in the entropy as opposed to the entropy values. So, what we mean to say is that the delta S of the system plus the delta S of surrounding is equal to 0 only if the process is reversible. If you have an irreversible process, which is more common in the universe, what we will have is delta S plus delta S of surrounding is higher than 0. Now, whether it is a reversible process or an irreversible process, the argument of Clausius was the surrounding is like always very huge in comparison to the system. So, instead of talking about number of ways of distribution in the surrounding, we can talk in terms of the heat that is added to the surrounding or minus of the heat that is added to the system, and define the entropy of the surrounding or the entropy change of the surrounding in terms of the heat that is added to the surrounding. So, with this particular idea, we can now define a reference state for the entropy as well, and that reference state is what we have earlier said is the 0 Kelvin state, right. However, we make a small detail to the argument there, and the detail is the following, that we say that now I can define the delta S of whether the system or a surrounding, but we are more concerned about the system in general. So, delta S can be written as the integration over dq reversible by T, where T is my temperature, and the integration is done over the initial and the final states. So, A is my initial state and B is the final state. Keep in mind that that definition is only true when the process is reversible. If on the other hand we have an irreversible process, what is always true is that delta S is higher than dq over T, where Q is now the heat added for the irreversible process. So, in general, the Q reversible is always higher than Q irreversible. Let us say, so if I am going from state A to state B, there is a reversible process of getting there, and there is only one reversible process, and there can be multiple irreversible processes for going from A to B, and for all those processes the heat that is being added is always higher, is always lower in comparison to the heat that is added in the case of a reversible process. So, now using this particular idea, if I define my initial state as the 0 Kelvin state, I can say that the entropy at any particular temperature minus entropy at 0 temperature, the 0 Kelvin temperature, is equal to 0 to T of dq reversible by T, and by the third law of thermodynamics, this particular reference state, the entropy at 0 Kelvin, is assumed to be 0. That is the state when we do not have any disorder in the system. As we discussed, this corresponds to a state where all the molecules are in their ground state, if I go with the Boltzmann probability argument. So, with this particular idea, I can now define the internal energy of the system in the following way. We have already established that the change in the internal energy is given by the heat added and the work done on the system, and in the differential form we can write this as du is equal to Tds minus Pdv. You can already see where it comes from, because I defined the entropy as the heat divided by temperature. So, therefore, T ds will become the heat that is being added, and P dV become the work that is done. There is a small point here to make, that both of these functions are actually path dependent if you look at it, but this guy is a state function. And although we have said that in general the delta S is higher than the dq by T going from A to B, in this expression we have put an equality sign that comes from some cancellations. I will not really get into them, but the way to understand that is there are two contributions to the change in the internal energy. One contribution relates to temperature and entropy, and one contribution relates to the pressure and the volume. And this temperature and entropy, they form like a pair that is called a conjugate variable, and similarly the pressure and the volume form a pair, and they are also called conjugate variable. So, with this idea of integration, let us say for example, if I am looking at the change in the internal energy of a process, I am basically looking at integration of what we have on the right hand side. So, you have integration of this and you have integration of this, that gives me integration of that. If I am looking from some state a to b and a to b. So, how will I compute this integral? So, you may notice that in the first integral on the right hand side we have t ds. So, s is the independent variable. So, t therefore should be written as a function of s, only then we can integrate with respect to the entropy s. Similarly, in the second expression we have p dv. So, pressure should be written as a function of volume. So, we have t as a function of s, p as a function of v, and the other way to say the same thing is that s and v, they become the independent variables in this particular expression, or they become what we know as natural variables. And in other words, we can say that our energy U is a function of, I use the word U, I use the U again as a function of S and V. I am looking at only a one component system. So, we are not concerned right now what is the effect of different species present, we will come to that later. In one component system you have only one component, and in this particular case I can write internal energy as a function of entropy and the volume. And why is that true? Because temperature and pressure does appear in the expression, but temperature has to be written as a function of entropy and pressure has to be written as a function of volume, because temperature is a conjugate variable of entropy, pressure is a conjugate variable of volume. There is one more way of saying this that is become important for the argument here. So, let us say for example, if I want to evaluate this particular expression, what do I have to do? For that particular process, I need to evaluate temperature as a function of entropy. That means, I need to conduct experiments at different entropy and find temperature in those conditions that will give me temperature as a function of entropy. Similarly, I need to do experiments at different volume and find pressures in those conditions, and therefore, I will get the function pressure as a function of the volume. And by doing that, what essentially we mean to say is that we should have an ability to control the entropy and volume. That means, by saying that I need to do experiments for different entropy and find temperature, what I mean to say that I should have a facility, I need to have a way in which I can conduct the experiment at different entropy, which means that I need to be able to control entropy at different values and find temperature at those values. Similarly, I need to have an ability to control the volume and find the pressure at those particular volume. That point becomes extremely important as we go along. So, now this brings us to the definition of a thermodynamic function, and the first function I am writing is the function U, that is the internal energy of the system, and this is a function of two natural variables S and V. And I also have the differential expression of the same thing, du is equal to TdS minus PdV. Okay. So, if you are with me so far, now what you can also see is, since u is a function of S and V, if I want to define derivatives of u, derivatives can be defined with respect to S and with respect to V, and these will be partial derivatives. So, for example, I can say dou u by dou S, that would be a partial derivative of u with respect to S, and this partial derivative by definition would mean that the other variable in the problem V is being held constant. So, although I have written it like V equal to constant here, in general if I write V in the subscript, it means that the volume is being held constant. And what is this equal to? You can see from there it is equal to the temperature T. In a similar manner, I can find dou U by dou V, where I am taking the derivative with respect to the volume, and this must be done by keeping S constant, and that should be equal to minus P. So, now I have a very nicely defined function, and I can define its derivatives, and we have pretty much all the toolbox that we need, provided we are able to control S and V in the problem. In general, that is not always true, because you may imagine the experiments you typically do in a thermodynamics laboratory. So, in those experiments, it is probably more easier to control temperatures as opposed to entropy, and in many cases it is easier to control pressure as opposed to volume. The volume may change in a process, but the pressure can be easily controlled. It may so happen. Similarly, entropy, first of all, entropy is rather vaguely defined because it relates to the disorder of the system. So, clearly controlling entropy is not something that comes very naturally as opposed to controlling temperature, because we can have some kind of a thermostat and we can control temperature. Controlling entropy is not as trivial as controlling temperature. So, here is what the other thermodynamics functions comes to our rescue, and we are going towards the definition of functions known as enthalpy and the free energies. And the way to do that is purely a mathematical way of representing these functions, and that refers as the Legendre transformation. So, what the Legendre transformation stands for is that if I have, for example, some function y of some variable x, then this function may have some shape, right. So, instead of computing the y at different value of x, I can get the same curve if I instead compute the slope of the function at different points x. And let me call that slope something like m of x. So, instead of writing yx, I can write in terms of m of x. So, if I know the slope at every point, I can hope to reconstruct the entire curve without knowing the function y itself. However, there is a small catch, and the catch is that for this particular slope, you can have actually a family of curve which are parallel to this particular curve. So, for example, all these curve, they will have the same value of m at this particular value of x if they are parallel to each other, right. So, therefore, apart from the slope, we also consider the intercept of the slope. That means, if I take the intercept, now this intercept is going to be a unique value for different curves in the picture. For example, if I have a curve here that will have a different intercept as opposed to the curve in the that I have drawn. So, therefore, instead of writing y as a function of x, I can write the function in terms of the intercept and the slope, because if I know the intercept and the slope, I can uniquely define the curve, and that is going to be the same curve as what we had, and this whole idea is what is known as a Legendre transformation. So, the way of doing that is the following. So, I can apply some geometry. So, what I can do is that I can find the slope. So, this value is my y and this is my phi. So, on the y we have y minus phi, and along the x we have x minus 0, and that is the definition of my slope m, which I can write as y minus phi is equal to m of x, and therefore, I can write my phi as y minus m of x. So, let us apply it in the case that we just had. So, I knew that du is TdS minus PdV, and we had dou u by dou s at constant volume is equal to T, and u is a function of s and v. So, let us say for example, I call this u as the function y that we have, and I call this s as the variable x that we have. Then for this choice of variables, this becomes my m, and therefore, I can find the corresponding phi as y minus mx, which is u minus m t multiplied by s. So, this means that instead of defining u, I can define a function u minus Ts, and u minus Ts is no longer going to be a function of s and v. Instead, u minus Ts is going to be a function of t and v. So, both y and x I am replacing with phi and m. So, this function, let me call this function f. So, this function is going to be a function of t and v. So, this becomes my phi and this becomes my m. This transformation that we have done is what is known as the Legendre transformation. So, I have changed the variables from yx to phi m, and we have pretty much the same description of the curve. But in terms of thermodynamics, you can see what advantage do have I got. The advantage I have got is now the natural variables are no longer s and v, the natural variables become t and v. So, therefore, the experiments I have to do now, I have to do at different temperatures and find entropy as those temperatures, as opposed to what I had earlier, where I was doing experiments at different entropy and computing temperatures at those entropy. So, now we have temperature as a controlling variable, earlier we had entropy as a controlling variable, and this particular function is what is known as the Helmholtz free energy, which is also a thermodynamic function just like the u. So, now I can also find the dF. By definition, we have dF is d of u minus Ts, which is du minus Tds minus sdt. If I do the derivative of Ts, it will be Tds minus Tds plus sdt. That is what we have here. And using this particular expression, what do I get is something like this. So, we have cancellations, and therefore, we establish that my dF is equal to minus s dt minus p dv, and we have successfully been able to define a new thermodynamic function that has temperature and volume as the controlling variable. And it should not come to you as a surprise that both of them have pretty much similar meaning. Both u and f have pretty much similar meaning, only the variable I am controlling has changed, because both represent the same curve. In one case I am using y and x, in other case I am using the intercept and the slope. Pretty much both are describing the same thermodynamics, only the variable I am writing in terms of is changing, only the natural variables are changing. everything else remains the same. So, now we can extend this idea and look at, for example, the other variable that I want to change. Let us say, for example, I again go back to this u and we have du as TdS minus PdV, but now instead of S, I want to replace the volume as the natural variable. So, u becomes again the y and v becomes my x, and dou u by dou v at constant entropy, that becomes minus p, which is my m, and I again have the same argument that I had in the previous example, that phi is y minus mx. Let us see what do I get by doing that. So, phi is y minus mx, y is my u, m is minus p, and x is my v, and so this becomes u plus pv, which we know as h, or the enthalpy. And just like what we have done earlier, we can again define the d of h, that is du plus pdv plus vdp, that is TdS minus pdv plus pdv plus vdp. Again we have a cancellation, and what do I get is TdS plus vdp. So, we have h defined as a function of s and p, that means the controlling variable has changed from v to p. So, now I can do experiments at different pressures and find volume. What I was doing earlier, I was doing experiments at different volume and finding the pressure. Again, it is a new thermodynamic function that we have defined, and it has the following differential form. So, if this is clear, we can extend this idea to multiple slopes together. So, just like what we did earlier was, we had y as a function of x, and I defined a slope and I defined an intercept phi, but in reality what you have is a multivariable function. So, you have u as a function of both s and v. That means, I need to define two slopes in terms of two variables that we have in the problem, x1 and x2. So, I can extend this idea, and what we then have, and you can derive it, is I can define the intercept as y minus sum over mj xj, where mj is the slope with respect to j variables. So, m1 is for x1, m2 is for x2, and this is summed over all variables in the problem. And you can see how it will be applied. So, in this case, if I start with this function u as a function of s and v, this becomes my y, this becomes my x1, this becomes my x2. I can define my m1 as dou u by dou s at a constant volume, and we knew that du is TdS minus PdV. So, m1 is equal to T, and m2 is dou u by dou v at constant s, that is equal to minus p, and therefore, I can define my phi as y, y is u, minus m1 x1, m1 is T and x1 is s, minus m2 x2. So, m2 is minus p, so we have a plus sign, and x2 is v, so we have v. So, we have defined a new thermodynamic function which is known as G, or the Gibbs free energy. And just like what we had done earlier, I can find dg, since u is equal to u minus Ts plus Pv, I can find dg as du minus Tds minus sdt plus Pdv plus Vdp, and du is equal to Tds minus Pdv, what we had earlier. Everything else remains same. Again we have some cancellations, and what we end up getting is minus sdt plus Vdp, and G therefore becomes a natural function of temperature and pressure. So, to summarize our discussion, we have defined 4 thermodynamic functions, and what was different in them was the controlling variables that we used. Otherwise, both are representing the same thermodynamics. It is simply coming from a mathematical operation, and these are U, H, F, G, namely internal energy, enthalpy, Helmholtz free energy, and Gibbs free energy. These are functions of different variables. U is a function of S and V, H is a function of S and P, F is a function of T and V, and G is a function of T and P. These are defined in differential form as du is equal to Tds minus Pdv, dH is equal to Tds plus Vdp, dF is equal to minus sdt minus Pdv, and dg is equal to minus sdt plus Vdp. We can also write H as U plus Pv, we can write F as U minus Ts, you can write G as U plus Pv minus Ts, or using the definition of enthalpy, we can write G as H minus Ts. So, this completes the thermodynamic functions for one component system. In the next lecture, we will see how this extends when we are looking at a multiple component system, a multi-component system, where we will also have one additional variable that we know as the chemical potential. So, with that I want to conclude here. Thank you and see you in next class.